All right. So I was going to talk about 128 here, which is using anything LM, but I checked and they've updated anything LM and moved everything around, so all my instructions of where the buttons are wrong. I'm going to have to rewrite this project. That tends to happen when things are new. People keep changing it too much. But let's talk about this one, embedding things with Burp, which is, you can use Google Colab, but these don't change so fast. So the point is here, BERT is a pre-trained model that understands something like 30,000 English words. And what we're going to do here is embed new words in and see how they preserve, how the meanings are encoded, which is interesting. Like I said, this was very important to me to understand how in the world large language models understood the meaning of words to some extent. And what they understand technically is the relative meaning of words. So you can, for example, show some of the words, like here's from 2000 to 2020. Here's just some of the words it knows. And as you can see, it knows a lot of English words. So now we can tokenize a sentence. After stealing money from the bank vault, the bank robber was seen fishing on the Mississippi River bank. Now the word bank appears 3 times in this sentence. And if you look at it, therefore, when it's tokenized, it gives it a random number, 2924, and every time bank appears, it's 2924. So that's a start. But if you embed them with BERT, BERT having been trained on English, then you can show the layers of your BERT and 13 layers and batches and tokens. BERT returns the layers. So this is embedding that into a pre-trained model, and now you can get the vectors. The vectors are the representations of those words that are used. And here, the vectors are actually, I think, 768 dimensions. So here's the first 5 parameters of each vector. So here's the word, after stealing money from the bank vault, the bank robber was seen fishing on the riverbank. And notice you can see the first 5 dimensions. The bank here has the first variable is, the first dimension is 3, the next one is -3, and then -1. And this one is very much the same, 3 minus 3 minus 1, because these 2 uses of the word bank have the same meaning. But this is the side of a river. It's completely different. So it's 1.5 minus 1 minus 0.5. So from context, the same way a human would, the LLM has detected that these 2 uses of the word bank mean the same thing, but this use of the word bank means something different. So it does not actually understand any of the words or know what they mean, but it does know when they appear in context next to other words and when they don't. And so it can deduce which meaning is actually used. So you can now calculate the cosine of the angle between those vectors in 768 dimensional space, which is a way to measure how similar words are. And so you can get the vector similarity for the different meanings of the word bank and for similar meanings of the word bank. And that's the game. So for the 2 banks that are similar, they're 94% similar, but for 2 different meanings, they're only 70% similar, and that's a measurement. That's the extent to which large language models actually understand the words. So now you can try this sentence. A boy becomes a man and a girl becomes a woman. And now you can calculate the difference between boy and man, and you can then calculate the difference between girl and woman, and you can calculate the difference between those 2 difference vectors, and you'll find that they're very similar. So relative meaning is encoded, and it even knows that if you take the difference between boy and man and add that to girl, you get woman. So that's the sense in which it understands anything. All right. Anyway, there's a few flags to find here, and that's all I wanted to show you there.